Okay, so let's look at examples. The electron in a hydrogen atom emits visible light in the Balmer series from the n equal to the 3 to n equal to the 2. Now for the part A, calculate the wavelength and the frequency of the emitted light. Okay. Okay, to compute for the wavelength, right? So let's use this Rydberg equation, this one. Okay, let's use this one. So we said that 1 over the wavelength lambda equal to the Rydberg constant, right? And the absolute value of the 1 over the Ni square minus the 1 over the Nf square. Okay, so now let's just put in the value. The RH, the Rydberg constant, is equal to this one. Okay, equal to this one for the Rydberg constant. And the absolute value of the 1 over the Ni. Okay, so from n equal to 3 to n equal to the 2, right? So this will be the I and this will be the final state, right? So the Ni equal to 3, we have the 3 square, and then minus the 1 over the Nf, so we have the 2 square here, and that's it. Okay, so the other just the algebra. You can just solve for the wavelength. So finally we can get that the wavelength here just equal to the 656 0.1 nanometer, which is the answer. Okay, so now you can see that this value, right, just in between the 300 nanometer and the 700 nanometer. It means that this is the visible light. Okay, making sense, right? Because in the Balmer series we have the visible light. So now for the frequency, the frequency equal to the speed of the light in the vacuum and then over the wavelength. So just plug in the number, right? We have 792,458 here, and over the wavelength we have the 656.1 times 10 to the negative 9. So then we can get that the frequency equal to the 4.569 times 10 to the 14 hertz. Okay, this is the frequency. Okay, so now we need to calculate the kinetic energy and the potential energies of the electron in the state n equal to the 3. Okay, so don't forget that for the n equal to 3, it's going to be the second excited state, right? For the n equal to 3, it is the second excited state here. Now we can do many things to find the kinetic energy and the potential energy. Okay, we can do just we can find the speed v and we can find the Rn, right? So if we know the speed v, we can find the kinetic energy, or if we know the Rn, we can find the electric potential energy. Okay, we can do this, but it just too much. Okay, but what I'm going to do is I'm going to compute for the En here. If I can find En, then I can just plug in here to find the Kn and the Un. Simple, right? Very easy. Okay, so what is the En? In this case, it's going to be the E3. Okay, the E3 equal to negative 13.606 electron volts and then per over T square, right? Which is equal to I don't remember. Let's see, 1.51, right? 1.51 electron volts. Okay, this is the E3. So here we can get that the K3, right? The kinetic energy of the electron, is going to be equal to, okay, so let's see, it's just equal to the absolute value of the En, right? So just equal to the absolute value of the E3, which is equal to the 1.51 electron volts. Okay, also for the U3, right, equal to the 2 times of the E3, 2 times of the E3, it is this one. Okay, so then just equal to the negative 3.02 electron volts, and that's it. So that's going to be answers. The next examples. Okay, a hydrogen atom emits an electromagnetic wave of the wavelength the 1.28 micrometer. Okay, so you can see that this type of the wavelength, right, it's just in the regime of what? So this is the, okay, infrared, right? It's just in the infrared. So it can be which series? For the infrared, it can be Parchens, brackets, and the Funs, right? So electron can move from the high end to n equal to the 3, to n equal to the 4, and to n equal to the 5. Okay, so that's with the possibility that we can get. Okay, find the initials and the final states of the electron. Okay, so that's the problem. We don't know the initial state. It can be n equal to 3, 4, or 5, and we don't know the final state, right? We don't know the final state as well. So how can we work on this one? Okay, the idea is we can use this Rydberg equation to solve. Okay, so the first thing is we need to try. Let's try n equal to the 3 first, and then just solve for the n for the nf, right? And then try n equal to 4 and solve for the nf, and try n equal to the 5 and solve for the nf, and etc. Okay, now this question, let's see. We have 1 over the lambda, okay, equal to the RH, right, the RH, and then, okay, 1 over the Ni square, right, and then minus the 1 over the Nf square, okay, and the absolute value. So now to work on this one, let's just do something. So it said that the hydrogen atom emits electromagnetic wave, right, of the wavelength equal to this. So it just emits the electromagnetic wave. So it means that the electron just transition from the large n then to the lower n. Okay, from the large n to the lower n. So in this case, if I just want to make this one to be the positive, okay, if I just want to make this one to be positive, then I need to switch these two terms together. Okay, I need to switch these two terms together, and then just take the absolute value out. So we have the 1 over the Nf square, and then minus the 1 over the Ni square, and that's it. Okay, so don't forget that the Nf is less than the Ni. It means that this term should be greater than this term. Okay, so it means that we have this to be the positive already. Okay, so now we said that we just want to try to plug in the Ni, right, and then find the Nf. Okay, so let's try to no, wait, we just want to, okay, we just want to plug in the Nf, okay, equal to the 3, 4, 5, and then try the Ni. Okay, sorry. Okay, so it should be something like this. So we said that if the Nf equal to 3, what is the Ni? If the Nf equal to the 4, what is the Ni, and etc. Then we can just rearrange the equation to get that the Ni is going to be equal to, okay, So if we move this to multiply with the lambda, right, and then move this to the left hand side and move this to the right hand side, we have the 1 over the nf square minus the 1 over the wavelength and then times the RH, right? But don't forget that on the left hand side we have the 1 over the nf square, okay? But we just want sorry, on the left hand side we have 1 over the ni square, but we just want the ni. Then it's gonna be negative 1 over 2, and that's it. Okay, this is what we get. So now let's try. Okay, let's try. Okay, so for the infrared, right, infrared, so the electron must move from the NEN to the n equal to the 3 to the 4 to the 5. So let's try the NF equal to the 3 first. Okay, the NF equal to 3, right? Then we have that the Ni is going to be equal to 1 over 3 square minus 1 over the wavelength, right? The wavelength just the 1.2x times 10 to the negative 6, and then times the Rydberg constant, right, which is equal to this value. Okay, and 1 over this value, and then total to the negative 1/2, like this. Okay, so if you use calculator, right, it's going to be equal to 5, and that's it. Okay, so it means that the electron just moved from n equal to the 5 to the n equal to the 3, and if we give the wavelength equal to this value, right, so this is going to be the answers. Okay, so now what happened? Okay, if you try, okay, just try it. Okay, if you try the NF equal to the 4, okay, so don't forget that, I mean, to get the infrared, right, we can have, I mean, the larger n, and then to the n equal to the 3, 4 and 5, right? So we try n equal to the 3 already, and we get the n equal to the 5. So let's try this one, NF equal to the 4. Okay, so let me copy this. Okay, 4, right, and square, this will be the minus 1/2. Okay, if you use calculator, you won't get any answer. Why? Because the whole thing here, right, it's just less than 1. Okay, so less than 1, so it means that we have the square root of, I mean, the number which is less than 1. Okay, so you will not guess the real number, you will guess the imaginary number. Okay, so it means that this is not going to work. So the answer is only this one. From the n equal to the 5, this is going to be the initial state. Okay, and then equal to the n equal to the 3, this is going to be the final state here. Okay, and this is the answers. Now another examples. Okay, find let me take note here, sorry, impossible. Okay, so now another example, find the quantum number n corresponding to the excited state of the helium ion. Okay, if on transition to the ground state that ion emits the 2 photons in the successions with the wavelengths 108.5 and 30.4 nanometer. Okay, so let's just draw the the energy level diagram first. So this one is not on the scale. Okay, it's not on the scale. Okay, so we say that we have n equal to the 1, n equal to the 2, n equal to the 3, and n equal to the 4, and etc. Right? So let's say that any n. Okay, let's say that it's with any n here. Okay, so this is n larger, n smaller, okay, and n equal to 1, like this. So then, okay, let's say that if we have electron, right, at this state, okay, so it just want to transition to the ground state, right? So again, we have many options, so we can go just from the n equal to n larger to n equal to the 1, right? So that's possible. But now in this question, it said that we have the 2 photons emitted. Okay, so it means that it can have from the n larger to the n smaller here. And now for the n smaller to the n equal to 1. Wait, sorry. Okay, from the n larger to the n smaller, and the n smaller to the n equal to the 1, right? So now the question is, we just want to find this quantum number n. Okay, so let's say n and the n palm. Okay, so this should be better. Let's say that this will be the n and the n palm and the n equal to the 1. Okay, so how, right? So how we solve for this one? Okay, the idea is, let's say that if the energy of n, this n, right, equal to the En, and the energy of n equal to the 1s equal to the E1, and let's say that the photons, the wavelength of the photons emitted here, right? Let's say that the wavelength equal to lambda 1, and the wavelength of the photons emitted here with equal to lambda 2, right? But still we don't know what is lambda 1 and lambda 2. Okay, it can be, lambda 1 can be this one or this one as well. For the lambda 2 can be this one or this one, right? We don't know yet. Okay, but then we just want to find this n, right? So how? Okay, so how? We can say that, okay, we can use kind of the conservation of energy to say that the energy of the electron at the state n, right, is going to be equal to the energy of the electron at the state n equal to the 1, and then plus the energy of these 2 photons, right? Because the energy of these photons equal to the difference of this energy, and the energy of these photons equal to the difference between these 2 energy levels, right? Then it's just equal to the Hc over the lambda 1 plus the Hc over the lambda 2. Okay, so now for the En, right? So we're talking about the helium ion. Okay, so we need to look at the hydrogen-like atom. We can use this equation to solve. Okay, we have this value and then multiply with the c square over the n square, right? Then we have the negative 13.606, and then times the c square. For the helium, the c equal to the 2, we have the 2 square here, and then over the n square, which is this n. Okay, equal to negative the 13.606, and then times 2 2 square, right? C square, and then over 1 square, okay, for this energy level, plus, okay, so now this value and this value in the unit of electron volts, right? So now I just want to use the Hc in the unit of electron volts as well, okay? So it's going to be the 1240, remember, electron volts times nanometer, and then over the wavelength, okay, let's say that the lambda 1 equal to this, okay? So we have the 108.5 nanometer for the lambda 1, plus now for the last term, right, we have the 1240 electron volts times nanometer, and then over, okay, so we use this one already, then we need to use this one, then times the 30.4 nanometer here, okay? Actually, let me just write out the EV. Okay, let me move it here. Then we can still have space. Let me change to red. Okay, like this. Okay, right. Okay, like this, right? So now that's it, right? So unit of the EV just cancel out, and unit of the nanometer just cancel out. So then finally we can just solve for the n. You will get that the n equal to 5, and that's it. Okay, the n equal to the 5. So this is going to be the answers. Okay. One thing about this is that you can find the n palm, right? You can find the n palm here by just trying to plug in this value and this value, and then to solve for the n palm. Okay, but in this case we are not interested in this one. We just want to only find the initial state n here.